Good afternoon and welcome to the webinar on compost carryover effects on soil quality, productivity, and cultivar selection in organic dryland wheat by Jennifer Reeve and Earl Creech of Utah State University. This is Alice Formiga from the eOrganic Community of Practice at eExtension. You can find all eOrganic articles, videos, and our many upcoming and recorded webinars on organic farming and research topics on our website at the link on your screen. I am very pleased to welcome Jennifer Reeve and Earl Creech today for our presentation. They're both from Utah State University. And with that, I'm just going to hand over the control now to our first speaker, who's Jennifer Reeve.
Thank you, Alice. Yes, so my name is Jennifer Reeve, and Dr. Earl Creech and I would like to take the opportunity today to tell you a little bit about our new multi-state project on long-term compost carryover and cover crop effects in dryland organic wheat. This is a new project, so we don't have a lot of new results to share with you today. However, what I would like to do is tell you about the work that was done initially, starting back in the early 1990s, that really laid the foundation for this new multi-state project. So these are just the universities involved in the new project. Earl will introduce the individual collaborators.
Muted.
So just to give you an idea of where the project is located, you can see here in the center of the screen with a little yellow thumb tag. That's where we are located in northern Utah, right near the Idaho border. And if we zoom in a little bit here, you can just see how marginal this land area is. We're just north of the Great Salt Lake. There's a lot of salt flats around us, and this is a very dry and also salt-affected area. It's desert, sagebrush desert. And here, if we zoom in a little bit more, you can see exactly where the plots are located on Google Earth. So this is what it looks like from street view, if you will. Again, you can see it's very remote, windswept, very low soil organic matter. You can see that the soil there is very pale colored. Naturally, it only has about 0.5% organic matter at most. The soil type is a calcareous thiocol silt loam. And for those of you who may be soil scientists, it's a sodic calci-zerept. So that means it has sodic properties, it's salt affected, can have moisture infiltration problems, and it's also very dry and calcareous, high pH. And yields here are completely driven by moisture availability. And so even in certified organic production, the growers use a wheat fallow rotation, and yields are they vary from 60 bushels per acre all the way down to maybe 5 bushels in a really bad year. So huge variability, and it's all driven by moisture, rainfall. That being said, Utah has over 30,000 acres of certified organic dryland wheat. And this represents 23% of Utah's dryland wheat acreage. So a huge proportion of Utah's dryland wheat is certified organic. And then obviously there's more certified organic wheat, similar systems in Colorado, Montana, Idaho, as well as further east in places such as North Dakota and Nebraska. So the original study was actually initiated back in 1994. One of the growers out in the Snowville area, this area I've just been showing you, he approached David Hall, the wheat breeder at Utah State University, with concerns that the quality as well as the yields of his wheat were falling. And so all the way back then, they wrote a proposal. It was funded by Western Sayre, and they initiated this study to look at the effects of compost on wheat yield and quality. So to quickly go through the the design, it's a completely randomized block design with 3 blocks with 2 treatments, or 3 replicates, 2 treatments. One was compost and the other was the control. The plot sizes were pretty small, but we were still able to find them again 15 years later. And the treatments really consisted of dairy manure plus straw bedding compost, and that was applied at a rate of 22 tons per acre dry weight in 1995. So here are some of the compost characteristics. You can see fair amount of nitrate, definitely quite a little, over 50.5% phosphorus, but typical for a dairy manure compost. So basically what we did then was in 2008, Dr. Hall and myself revisited these plots. You can see all these rows of telephone poles. Dr. Hall had used these telephone poles to triangulate off, so we were able to locate the corners of these plots all those years later. Here's a picture of Dr. Hall and my student, Davey Olson, measuring out the plots. This would have been in May, so early in spring. So this is what we found. So these numbers are actually in kilograms per hectare, and I'll show you the bushels per acre comparison later on. But here along the top we have the original yield, so the compost that was applied in 1995, and then they actually did the same, they repeated the experiment on the other side of the road in 1997. But we weren't able to locate those second plots. But you can see that compared to the control, in 1995, there was over double the yield in response to this compost. So a pretty phenomenal effect. And 2 years later, in 2007, that effect was still there. Very little difference between those 2 years. However, despite this really dramatic yield increase in response to compost application, when they went through the numbers, the economics just not did pan out. It was just too expensive to haul compost all the way out into these remote locations. However, when we visited again in 2008, what we discovered was that the yields of winter wheat was still double in 2008 compared to the control. And then 2 years later, there's a gap between the years because that's where the fallow was, right? So the next cropping year was 2010, and here again you can see that the yields were double. The difference, drastic difference in yield between years is attributed to this rainfall, rate of rainfall that we were talking about earlier. And these differences were significant. So these little symbols, the crosses here, are significant at 0.05, and the double cross is significant at the 0.01 level, etc. So we also took soil samples and looked at the soil properties. Again, you're seeing the results from the 2008 cropping season and the 2010 cropping season. Here along the top we have Olson P, which is the available P extract done for calcareous soils. And you can see that phosphorus in the top, this is just the top 5 centimeters, is significantly higher than the control. So all these years later, we're definitely seeing elevated soil phosphorus in response to the compost. And same for potassium. However, potassium is not limited in these environments, and so the potassium effect is perhaps of less significant agronomically. Now, when we look at the dehydrogenase activity, this is actually an enzyme that we like to measure as perhaps as a proxy for microbial activity, and you can see that in 2008 there were no differences. This was actually a drier year. In 2010, however, when it was a little bit wetter, we did see differences in dehydrogenase enzyme activity between the compost and control treatments. Similarly with acid and alkaline phosphatase activity, this enzyme associated with mineralization of organic phosphorus. You can see that the composted plots were significantly higher in both years for the acid phosphatase and just the alkaline phosphatase in 2010. We saw no differences in microbial biomass or in soil respiration. So now if we look at soil organic carbon, which is the top value here along the top, again you can see that soil organic carbon is doubled in the top 5 centimeters. And that literally, to translate that into percents, that's a difference between 0.5% and 1%. So the compost was affecting soil organic matter 14, 16, and as we now know, 20 years afterwards, after this single compost application. We saw no differences in soil nitrate and ammonium, and very few differences in trace elements. There was slightly significant elevated zinc in the top 5 centimeters. So now if we go down a little bit to the next depth increment, which is 5 to 10 centimeters, you can see that many of these effects are still visible. There's still a strong phosphorus effect of compost in both years, 2008 and 2010. Also of Olsen potassium. We see the effect of dehydrogenase activity in 2010, but we don't see any effect of phosphatase on that lower depth. And again, no differences in microbial activity, microbial biomass or soil respiration. The organic carbon, the soil organic matter, is still almost double at that depth. However, it was not significantly different. The variability was starting to affect the significance of the results there. And then finally, we looked at the 10 to 30 centimeter depth increment. And this is interesting because if you look at the Olsen P level, there's no difference across the board, but look how low that available Olsen P is. Just to put this in perspective, soil test recommendations typically say that 15 parts per million is low. So this is 5 parts per million is very, very low. And so this is why we actually think that one of the reasons we think that the compost might be having such long-term effects on wheat yield is that it's the phosphorus is staying available in those top layers for plant uptake in a soil type that is naturally very, very low in available soil phosphorus. And of course, one of the reasons that soil phosphorus is so low in these kinds of soils is because of the calcium carbonates, significant calcium carbonates in these soils. So the pH, I should have mentioned, is about 8.2, slightly above 8. But we did not see any differences on soil properties below 10 centimeters. And again, no differences in soil carbon either. So just to put that in a little bit of perspective, what does this mean? I think that we attribute a lot of these effects to the soil phosphorus effect, but perhaps also to increased moisture holding capacity due to that additional soil carbon in the top layers. But one question we don't really know is, is it the original compost that's sticking around for 14, 16, 20 years, or is it just, are we kind of priming the system? By adding this compost, we're increasing yields and increasing root growth and increasing residue return to the soil, and all of that is sort of creating a kind of a snowball effect that's then priming the system, if you were, and improving yields down the line in the long term. So just in case any of you were wondering if this is all fluke, because these are pretty dramatic results to see an effect of compost, a single application of compost lasting so many years, we went on Google Earth and we're actually able to pull up a picture, an image of the plots taken from space, and they're still there. The 3 compost plots, you see those, the little checkerboard inside the white circle, those are the plots, and they're still very much intact all this time later. And just to zoom out a little bit, there the plots, the yellow markers actually where our plots were located, and these ones you see are the ones across the street. You can see that they're very distinctive. There's no other similar landforms in the vicinity, so these are definitely the composted areas. And this is a picture of what it looked like from the ground. You could really see the difference. This is the, a control plot in the foreground, and then the denser wheat in the background is one of the compost plots. This picture would have been taken in 2008 or 10, I don't recall. So what we did next was we wanted to figure out the cumulative yield gain since 1995 so that we could start to think about the economics of applying compost to dryland wheat in northern Utah. Obviously, the original study, despite the initial high yield effect, they were not able to make the numbers work. It was just too expensive to truck compost all that distance. So what we did here, so you can see along the left of your screen the years starting in 1995 going all the way through to 2010, and the rotation, or the crop that was grown, wheat except for one crop of safflower in 1998, and then back to wheat. And the missing years represent the fallow years in the rotation. So the next column over, we have Y0 represents the control yield, the yield with 0 compost applied. And so 22 bushels was the control yield from those plots I was just showing you the data from, and compared to 16 bushels in 1997, and then the numbers with the stars underneath, that represents the grower's combine yields for that field, because obviously we weren't monitoring the study for all these years, and then we came back in 2008, we just had 3 bushel per acre yield in 2008 and 13 in 2010. But again, you can see how much it varies year to year, and this is purely a rainfall moisture event. So then the Y50 is the measured yield response of compost, and so in 1995 the compost response was 56 bushels per acre, 51 bushels in 1997, and then 7 and 23 in 2008 and 2010. And what we needed to do then is estimate the yield benefit in those missing years. So we basically created a regression model and used a model to come up with the estimate of what those yields would have been. So that's Y50 estimate. And then what we did is we basically subtracted the control values, the Y0 values, from the Y50 values to come up with the cumulative yield, the difference between the control, what you gained from adding compost. And we added all that up over the years. So now, what we found was that between 1995 and 2010, we had a cumulative yield gain in response to compost of 152 bushels per acre, or 5.56 tons per acre. The cost of the closest source of compost that we found at the time was $154 per ton. And at 22 tons per acre, that was a cost of $3,394. In 2009, the average price of organic wheat was $330 a ton. It's since gone up quite a bit, by the way. And so we just multiplied the cost of the wheat with the tons compost, and or the yield gain, sorry, the price with the yield gain, and we came up with $1,505 profit as a response to, well, I guess that's not really profit, but the grain yield was worth $1,505 in response to that compost application. I hope I'm being clear. However, the cost of the compost was almost as much. And so then what we did was we because obviously we were still seeing differences in yield 15 years later, 16 years later, we modeled the carryover out to infinity, and so that would and based on that, you know, the carryover, the drawdown of that compost effect, we estimated that maybe the total value of that compost would be 9.77 tons per acre yield gain. And so the total estimated yield gain then was worth about $3,000. So compost carryover is evident on soil quality, soil fertility, and yield of winter wheat 16 years after application. We now know that we've actually got additional data 20 years after application, and those values, the yield differences are still there. At current wheat prices, this carryover is insufficient to justify application of purchased compost at the rate of 22 tons per acre. Further research is needed to measure long-term carryover of lower applications rates on yield, or finding a cheaper source of compost. And so that was really then what spurred us to think, well, how can we're so close, you know, the profit from the wheat in 20 years or 16 years just about breaks even, right? It was a little bit, the compost was still cost a little bit more than the wheat. It was likely going to be profitable over the lifetime, the projected lifetime of that compost carryover. However, 16 years is still a long, long time to break even. And that's not going to work for most growers. So our next question is, well, yeah, how can we make this work? Can we use lower rates and have this effect still work? Can we use, find cheaper, more local sources of compost? What can we do? And so at this point, I'd like to turn it over to Earl Creech to talk about the new project that we received funding for just last year, and what we plan to do to try and answer some of these questions.
All right. It's good to be with you. My name's Earl Creech. I'm the extension agronomist at Utah State University. And I just wanted to kind of build on some of the background that Jennifer gave you and just look forward a little bit and talk about what we plan to do with this information. So as Jennifer discussed, dryland organic wheat is really important in Utah, and we are, and in a lot of states in the West, there's a lot of acres of it that are grown, but wheat yields in the West are severely constrained by moisture. And from the data you saw, presented by Jennifer, if these growers can get 20 bushels per acre per year, they're ecstatic. And as a result, there's not a whole lot of money to plow back into crop inputs in order to increase our yields. And so yields and quality of organic dryland wheat have suffered over time, and a lot of our growers are really struggling to stay in business. And so this project is in response to the challenges of these growers. Almost by accident, we discovered that the extremely long life of compost in these dryland wheat systems, and it's caused us to step back and think that maybe this could provide a solution to the low fertility problems that we're facing on these drylands. And so we wrote a grant to the USDA OREI program, and it's comprised, and our team is listed here on this slide. And so we have four universities, Utah State, Washington State, University of Wyoming, along with Oregon State, to help us with some of the electronic dissemination of these messages, of the work that we're doing. And the individual folks involved include folks like me. I'm an agronomist, and Jennifer and Astrid, they're soil scientists. David is a plant breeder. Kenda Curtis is an economist, and we have folks with those types of backgrounds spread across those universities. But together, the Utah State, Washington State, and Wyoming, the states of Utah, Washington, and Wyoming make up about 26% of the organic wheat acreage in the United States. And so three pretty big players in the organic wheat world. So as we thought
Muted.
barriers to adoption of using a single application of compost in dryland organic wheat, one of the biggies would be if there's a way that we can cut the rate in order to make it more economical. And so, and also maybe look at using cover crops or other creative measures for helping to address fertility. So these are the objectives for our OREI project, and you can take a look at those. But really, the biggie is taking that initial rate that was in that the work that Jennifer presented, and then cutting it back incrementally to try to find rates that would be a lot more economical to apply, but may still have the same effect. And also, we wanted to be able to expand this work geographically. We wanted to know whether it just happened to be this one field where this result happened, or if we could expand it to other fields within the state of Utah, or if we could expand it to other areas in the United States where organic wheat is grown and see a similar response. And so those are kind of the main objectives that we had in this project. So this is just a quick rundown of one of the trials that we've established. This is on a USU experiment station farm. You can see that third bullet point down. The fertility input, we applied compost at the 0 would be the control. We also applied compost at 5, 10, and 20 tons per acre. And so we've kind of reduced it to just a fraction of what we had initially applied, with the hopes that maybe we can see a positive economic response. We also are looking at cover crops in this trial, just seeing if we can maybe grow something on the land that can contribute to the fertility without depleting the moisture so bad. And that's something that we really struggle with in these low rainfall type environments, is simply growing. We can only, let me back up. For those of you who are not familiar, in Utah, in dryland, we grow wheat in a wheat fallow type system, and so we grow one wheat crop every 2 years, and we use the fallow year to collect water that we then use to grow a subsequent wheat crop the next year. And so we don't receive enough moisture to grow wheat in any 1 year, but we do over 2 years. So when you introduce a cover crop into these systems, you can deplete soil moisture, which is like gold to these farmers. And but we're hoping that maybe through some creative use of cover crops that we may be able to get a positive result. Let's go on to the next slide. So this is just one, each of these experiments has 4 replications. This is 1 replication. You can kind of see that there's a lot of treatment comparisons that we're going to be making. Each one of those little squares is a different treatment, and you can multiply that by 4 and you'll have the number of plots at each given site. And so we'll generate a lot of data and hopefully be able to get some answers for these growers. This is another trial that's located on a grower's field, and again, there's just a lot of treatment comparisons that we can look at to generate the information that we need to help these growers to make management recommendations. So next steps, one is we'd like to continue monitoring the sites on Richard Grover's farm. We have new trials at the USU Experiment Station farm, and also a new one at Richard Grover's farm. We also have additional grower cooperators in Utah, in addition to Richard and David Deacon and David Smith, and there are grower cooperators in Washington and Wyoming that are also working with us on this project. And each of these trials will be replicated in other states. And we're just hoping that we can get a better understanding of what's going on here, and hopefully be able to come up with ways that we can update our management recommendations for dryland organic wheat and help to give these growers answers and help them to remain profitable and be able to stay in business. So I think that is it. There's some acknowledgments that you can read through, but Alice, I think that's basically what we wanted to get across today.
Unmuted.
Okay, thank you very much. With that, let's just move on to some questions. We have a question about the compost. If you could tell us a little bit about the quality of the compost and also regarding microorganisms in the compost.
Well, we didn't actually measure that, and so I cannot tell you. However, it was a dairy manure compost, and we made it here at USU. From dairy manure plus straw bedding, and so it was, maybe a little bit low in nitrogen compared to a chicken manure compost, but I think, I can't see my slides, it was about 1% nitrogen, no, nearly 2% nitrogen, about 0.5% phosphorus, and I imagine lots of microorganisms, even though we didn't actually measure that. But pretty much all good cured compost would have plenty of microorganisms present.
Okay, thank you. Here's another question. What cover crops and alternative crop rotations will you be using in the new project?
Earl, would you like to answer that one?
Jennifer, you're the expert.
I don't know. Well, we didn't present it today, but Dr. Hall, as well as some of our grower cooperators, have been testing a number of different cover crops over the years, and obviously we would like to have a nitrogen fixing cover crop because nitrogen and phosphorus even are really our two limiting nutrients in these systems. So a nitrogen fixing cover crop will fix nitrogen and maybe even help solubilize phosphorus in the soil, because legumes secrete organic acids from their roots, and this can sometimes help make soil phosphorus a little bit more available. And so basically, based on these prior trials that we have done and various other cooperators have done, we narrowed it down to hairy vetch and Austrian winter pea. Both of those do really pretty well, and with the problem with the fall planting is that often we don't have the moisture, especially after coming out of a harvested wheat situation. The soil is very, very dry and depleted of soil moisture, and so getting them to come up in the fall is pretty challenging. So we've explored spring plantings and that's obviously challenging too, because if there's a heavy snow cover or it's a really wet spring, it's hard to get into the field early enough. So we're going to be exploring dormant seeding techniques, and then to see if maybe we could get a good stand established that way, up early in the spring as soon as the snow melts, so that we could terminate it early, so that we're not going into the summer and depleting our soil moisture, as Earl mentioned. In terms of alternative crop rotations, including safflower in the rotation is definitely a possibility. However, organic wheat is so valuable that our growers are really reluctant to put alternative crops into their rotation. I think it would be great if we could somehow include some animals in the rotation. In fact, one of our cooperators does do this. He makes his land available to a neighboring cattle farmer. Obviously, cattle are a lot of work, and many of our growers don't have the facilities or means to start cattle operations themselves. But I think perhaps with some land sharing efforts, maybe we could, you could include maybe some kind of forage in the rotation, or at least have a grazing component. I don't know. To be honest, when we've asked for feedback, the problem is that wheat is so valuable. As soon as you reduce the number of wheat crops in the rotation, you seriously undermine the profitability of the system. And this is a marginal system anyway, just because of the huge variability in yield. And so the growers are really only making a profit maybe every 6 years. Obviously, it's not every season by any means. So it's a challenge. We've wondered about perennial wheat. That's one that I would really like to explore, because I think if we could get a perennial wheat developed, and I know people are working on this, maybe, with the deeper root system that actually harvests soil moisture over a greater length of growing season, maybe that would help make these systems a little bit more sustainable.
Okay, this person has 2 questions. So the first one is, can you share with us the model you have used to estimate yield?
I'm a little unclear what you mean. You mean how we filled in the missing? It's in our paper. This is published in Soil Science Society of American Journal in 2012. I assume you mean the model where we projected the compost yield response in those missing years. Is that what you're asking me?
Okay, if you're the questioner, if you could type that in to clarify, that would be great. Let's see. Meanwhile, maybe we can talk about the second question, which is, do you surface apply the compost?
We do, but we also then disc it in, because it's very windy out there and we don't want to lose it. So, okay.
Let's see. I guess while we're waiting for additional clarification on the yield question, we'll go with another question, and that is, what about other high-value grains like quinoa, millet, amaranth, and teff?
Earl, would you like to?
I will go ahead and take that question. The growers in Utah have a tremendous amount of interest in some of these alternative grain crops, and in the we're presently doing quite a bit of work on another OREI project with quinoa on irrigated land. We haven't done anything on dry land with quinoa. I know it grows in pretty dry areas in its native land, but we're unsure of how it would respond here in Utah at this time. Something like teff. This ground would be way too dry for teff. We've done quite a bit of work with this crop on irrigated ground, And even though teff is fairly drought tolerant and doesn't require a whole lot of water, it does require some. And the areas where they're growing dryland organic wheat are generally pretty much nil when it comes to water precipitation during the growing season. It's mostly winter moisture that comes in the form of snow, and so teff, where it would be planted about the first part of June, it would never really get exposed to enough water to bring it up and get it going. So no, we're interested in these alternative crops, and just in these environments where organic wheat is grown, there's just nothing that can compete with organic wheat.
Okay. Meanwhile, the questioner who asked about the yield model said that he or she wanted to know the Y50, how you got the Y50 estimate.
Yes. So in the years where we actually measured it, that was a measured value from our plots. But the missing years we estimated with a model. And the model is pretty complicated. I've actually got it in front of me here in the paper, but it appears in full in the paper. And if the questioner would like to send me an email, I'd be more than happy to send a copy of the paper so that they could read through that.
Okay, that sounds great.
See how we do it. Yeah.
Okay, and if you don't have Jennifer's email, I'll be very glad to put you in touch. So you'll get multiple emails about the webinar, so feel free to ask that question if you have trouble getting in touch. But Jennifer has a website, so it should be pretty easy to find in Google. Let's see, so what percentage of organic matter do you have in the test soils, and do you expect that an increase of organic matter do you expect an increase? In my opinion, that would increase the capacity of the soil to capture water.
Yes, exactly. And so if you scroll back or look through the handout, you will see that soil carbon, we use organic carbon as a proxy for organic matter. So obviously those are not exactly the same thing, but organic matter is mostly organic carbon. And so you could see that the native organic carbon levels, the uncomposted organic carbon levels were at only 0.5%, 0.5% in the top 5 centimeters, while the composted soils were 1% 16 years later. So yes, the compost is contributing to soil carbon, long-term soil carbon, and that could definitely be partly responsible for these increased yields. In fact, an earlier study that a student of Dr. Hall's did, they actually they modeled they tried to partition the proportion of the yield response into nutrient effects versus moisture effects, and they concluded it was about 50-50. So in other words, half of the yield response was due to increased moisture. And we will be looking at that too. We have at our Blue Creek site, we have soil moisture access tubes installed down to a depth of 6 feet. So we'll be measuring soil moisture in response to all our different treatments, compost rates and cover crops. And we hope to, we also have a new PhD student who's going to be looking at the carbon chemistry, trying to find out if some of this carbon is old carbon that's maybe organic acid coatings on soil particles or something like that, or if it's purely new carbon from this kind of snowball effect that I was describing, from the increased root and shoot biomass returning to the soil every year.
So let's see, we don't have any more questions. Thank you very much, Earl and Jennifer, for taking the time to talk with us today, and we look forward to future webinars about this project when you have additional results.